Hello guys, welcome back to my channel Gamma Di Gamma. So in the previous video, I believe I introduced a Taylor and Laurent series, at least in terms of complex functions. Again, continuing with my complex analysis sort of video streak. In this video, I'm going to do the specific example of finding the coefficients of the Taylor and Laurent series so that you see how the coefficients sort of depend on the region of expansion or where we sort of choose our contour to be, region to be. So let's get started. Consider this function f of z is 1 over z minus a plus 1 over z minus b, which we can sort of take a common denominator to get z minus a, z minus b, and that numerator. Well, notice that it is analytic everywhere except at points z equals a and z equals b. Okay, so what are we gonna do? Well, we can sort of plot it out. Let's say we want to expand it z equals z naught. So let's draw this sort of diagram in the complex plane. So say we have like z naught here at the center. We have some locus for point A, some another locus for point B. Okay. Well, what we can do is let's first start with like regions enclosed inside z naught and a. So for that, I'm just going to draw an arbitrary contour in that region. Again, convention dictates we want it to go anti-clockwise. Call this C. If you remember the formula, the general formula that I derived in the last video for the coefficient of the Laurent series is basically this: dz prime fz prime over z prime minus z naught n plus first power. So this was the formula. Let me just sort of plug everything into this formula. So if I sort of plug everything in, I have 1 over 2 pi I contour integral about C. Now we have defined C. dz prime 2z prime minus a minus b divided by z prime minus a, z prime minus b, z prime minus z naught to the n plus first power. Okay, what we can do is we can sort of break it up in two different cases. So let me just call this case 1 like the title, this entire thing, because we're just considering region that's enclosed within A. And I'm sort of further dividing it in two cases. So this is the negative case. So the negative case, if n is negative, this term will be in the numerator, or it will be 1 for say a negative 1. It will be the power will be 0, which will make this entire thing 1. Or otherwise, for like other negative powers which are lower, we're gonna make this term go in the numerator forcibly. It's going to be some integer power in the numerator. So we don't really need to worry about this term in the denominator for this case. The only sort of trouble causing points are at z is equal to a and z is equal to b. But if you notice this, the region enclosed within the contour, because that's the region where this expansion will be valid, because again these contour integrals are directly connected to the region enclosed by them by the integral theorems Cauchy-Goursa and Cauchy integral formula by those theorems. So those troublemaker points, z is equal to a, z is equal to b, are not enclosed, because that's how we define the contour, and that's exactly why we need to differentiate between case 1, case 2 and case 3. That's because this region enclosed will, what it encloses, what it doesn't enclose, we need to worry about those in the future. So since it doesn't have these troublemaker singularity points, we can just set this entire thing to 0 by Cauchy-Goursa, because there's literally no singularity point. So the entire contour integral is just 0. Please watch my video on Cauchy-Goursa if you sort of don't agree with me on this. Okay, let's do the other one. For n is greater than or equal to 0, so the positive case, which means this term will remain in the denominator and will create a problem, because z0 is now, because of this expression, will create a problem because z0 is in the denominator. There's no other trouble creating terms. A and b are outside, so we only need to worry about z0. If you notice sort of the makeup of this entire thing, f of z prime over z prime minus z0 to the n plus 1, this actually looks like, as long as z0 is inside the region, which it will be for n greater than or equal to 0, this looks like the nth derivative of the Cauchy integral formula. Please go back to that video if you don't or remember or don't believe me. Except we have to multiply by a 2 pi I. So n factorial was like sort of the normalizing thing. Nth derivative of f of z prime, which is basically 2z minus a minus b divided by z minus a times z minus b, taken at the point z0, the troublemaking point. If you can cancel this out, well, since this is basically 1 over z minus a plus 1 over z minus b, we can notice a pattern for the nth derivative, and we actually get negative 1 over a minus z0, the n plus first power, minus 1 over b minus z0 to the n plus first power, for again n equal to or greater than 0. You can check this out, pause the video. This is just basic calculus and arithmetic. Okay, so you see for the negative powers it's 0, positive it's greater than or equal, for the greater than or equal to case we have some finite value for this coefficient, which means we can represent f of z, which is nothing but 1 over z minus a plus 1 over z minus b, as sum n equals 0 to infinity, using the definition of the Laurent series, general Laurent series, to get 1 over a minus z0 to the n plus first power plus, I've taken the negative outside, 1 over b minus z0 n plus first power, and since this was just the coefficient, we need to multiply by the polynomial part, z minus z0 to the nth power. So if you see, there's only positive powers of z minus z0. There's no negative power. This is a pure Taylor series. Since this is a pure Taylor series, you could also derive this coefficient using the geometric series approach by sort of factorizing something out in the denominator and again using the formula for the geometric series, and then sort of deriving this. You would have gotten the same answer, because again this is a pure Taylor series. Now let's talk a little about the region of convergence quickly. The region of convergence is the region where all the steps we've taken, or sort of the coefficients we've got, hold valid. So Cn for negative n should be 0, and Cn for positive n, positive or 0n, should be equal to this guy here. So where is that region? Well, that region is, it will be basically, yes, this white shaded part definitely, but it'll extend until from z0 to a, because if you go beyond a, your Cn will no longer be 0, because now you can't use Cauchy-Goursa. z prime minus a will be a trouble creating point, so you have to deform the contour, so it won't be valid anymore. Even for this guy, the positive or 0 n, we would sort of want to deform it in a different way. So this region of convergence is from z0 to a, this entire thing until now. I won't include the boundary because a boundary, topologically speaking, is neither inside nor outside, and moreover we want like the region enclosed, right? And boundaries are sort of out of bounds for us. So let me just write the region of convergence. Z minus z0, absolute value or the magnitude, is less than a, which is basically saying that you center at z0 and you basically are in this disk up till a, and you're not having an equal to because we don't want to include the boundary. Again, this is a disk because it's a region, it's not just one circle, not one line. I hope this kind of makes sense. This was probably the easiest case we will deal with. We have to deal with other cases, case 2 and case 3, because we will keep taking in these singularity points and deform the contour. And spoiler alert, Cauchy-Gursa won't help us all the time. So see you on a fresh page with another case. Okay, let's talk about the second case. In this case, we have, well, everything's the same, like z0's at the center. Again, we're expanding about the same guy. We have this line of A, circle of A. That's a interesting name to give it. And then we're defining a contour. So, like, we didn't include A in the previous case. We are now. Again, going counterclockwise. And then the circle of B, which we are excluding to be left out as a separate case. This is point B, assuming. Again, we can write the same formula again. Cn is 1 over 2 pi I, contour integral around C, dz prime z prime minus a minus b, divided by z prime minus a, z prime minus b, z prime minus z0 to the n plus first power. Again, we can divide the powers of n. Let's look at the negative first. If you look at the negative, well, z minus this z prime minus z0 guy shouldn't create a problem like before. Only thing we need to worry about is this a point, and for a point we just use the Cauchy integral formula, no derivative of it, just the normal Cauchy integral formula. So we have 1 over 2 pi I multiply by 2 pi I, if you remember the formula, and then plug in a. So we have 2a minus b divided by a minus b times a minus z0 to the n plus first power. So this cancels out. We have a minus b that cancels out with the denominator. We just simply have 1 over a minus z0 to the n plus first power. And that is your negative coefficient. It's not 0, so that's why it's important to sort of, look at the region you're in and what singularities it contains, because that will completely change what the Laurent series looks like. In the previous case, it was a pure Taylor series because its negative n coefficient was 0, but now it's not, so it will be a mixed Laurent series with negative and positive powers. Let's look at now the positive semi-definite case, the n is greater than or equal to 0 case. Okay, let's see. Well, the thing is, for n greater than or equal to 0, z0 will create a problem, so will a. So we need to account for two singularities, and a really good way to do this, if you've seen my previous videos on this topic, is to deform the contour. So your contour C was like a little bit like this. Again, excuse my drawing, I'm trying to do my best here. So we would sort of encircle around point A, then sort of go around and then circle around the Z naught. So we again obeying sort of this anti-clockwise direction even when we're like going inside, taking a detour inside. And then of course we have the B circle as outside, just sitting there, not doing anything to our contour. And this is where this detour was for Z naught, because even that will create a problem for the positive semi-definite case. So it's important to notice here in this entire diagram that contour integral over C dz prime, which is basically this external circle, this will become a complete circle when I take the limit that this gap goes to 0. And same thing here, which is basically what we do without writing for every contour deformation idea. So with f of z prime, z prime minus z naught to the n plus first, and then since when we take this, call this C1 and call this C2, we go in C1, we're doing in a clockwise direction, we have to take in a negative by convention. So C1, same integrand dz prime fz prime over z prime minus z naught to the n plus first, minus, well again clockwise for C2, dz prime f of z prime over z prime minus z naught n plus first. All of this is equal to, well, what's the region enclosed? Region enclosed is the region where the function is analytic. There are no discontinuities, there are no singularity points. So by Cauchy-Goursat it will be 0. And this is precisely why contour deformation is sort of an unsaid idea that works for many singularity points like this. That's because we know what the right hand side is going to be. It's going to be 0 by Cauchy-Goursat. So we can sort of see, we can substitute instead of say contour integral over C of 1 over 2 pi, we can just multiply that out. dz prime f of z prime over z prime minus z naught to the n plus 1 is nothing but 1 over 2 pi I integral over C1 dz prime f of z prime over z prime minus z naught to the n plus first plus 1 over 2 pi I integral over C2 dz prime f of z prime over z prime minus z naught to the n plus 1. That's why, you know, we can substitute in place of integral over C, because this integral was for the sort of the coefficients. We need to make a substitution. Fair enough. So what we can do is we can evaluate these guys separately. You notice that this is Cn. You notice that C1, for C1, and it's going to look like, let me just do a quick substitution to z prime or dz prime minus a minus b, z prime minus a, z prime minus b, z prime minus z naught to the n plus first. Well, noticing this guy, well, C1 just encloses A, so we can use Cauchy integral formula for A. We get a result, a similar result as we got for Cn for negative n. Let me just write that 1 over A minus z naught to the n plus first. I won't bother writing out everything for C2, but notice that only singularity point it encloses is z naught, and z naught has this n plus 1 power after substituting it into for f of z prime. So we notice this is just the nth derivative of the Cauchy integral formula. So just like we had before for case 1, divide by n factorial, nth derivative of 1 over z minus a plus 1 over z minus b taken at z is equal to z naught. So we have 1 over a minus z naught to the n plus first power minus 1 over a minus z naught, using the result from case 1, minus 1 over b minus z naught to the n plus 1, and see how wonderfully this cancels out. So Cn is just negative 1 over b minus z naught to the n plus first. And now, since we have the coefficients for the positive semi-definite and the negative case, let's write the expansion down. So let's write the expansion f of z, which is 1 over z minus a plus 1 over z minus b, can be expressed as, well, let's break them up. So let's write the negative guys first. So negative infinity to minus 1. Again, I'm doing the right order in this time. A minus z naught, n plus first, and then z minus z naught to the n, because it's again a series, power series. This was just the coefficient. Plus then the positive semi-definite case. And we have a negative 1 over b minus z naught, n plus first power, z minus z naught to the n. And this is a proper Laurent series expansion, because you notice the positive and negative power terms here. So now you see why these are important, because when we didn't enclose any singularities, we basically use the same idea that we would have used for, say, a real valued function. But now when we are actually enclosing singularities in our contour, that we are actually concerned with stuff that's actually inside, and we are actually utilizing the idea of Laurent series by taking or obtaining negative power terms and coefficients for those negative power terms. Now let's talk about the region of convergence like we did for case 1. And again, this is an important discussion because that enables us to know when to use what going forward. So talking of the region of convergence, let's see how far these assumptions hold. Well, you see, we can't take the contour inside A, because that will just give us case 1. So our radius has to be greater than A. We know that for sure. We can't sort of enclose B, because then our deformation would look different. We would have, instead of just C1, C2, we would have C1, C2 and C3, where C3 is for the singularity at B. So we can't sort of exceed B. We can't go inside A. So we're stuck between A and B, which is basically sort of this weird region. It's probably hard to sort of sketch here. Let's see if I can do a good job. Let it be. I won't draw it. I hope you see the idea. I'll write the inequality. So z minus z naught is magnitude is trapped between A and B. That's the sort of like an annulus, a ring. Assume this is A. Assume this is B. Z naught's at the center. So we are sort of trapped between A and B to get like a ring, which is like sort of a discus, like not even a complete disc. A disc has the center region. We don't have the case 1 region, because that would bring us back to case 1. We're in case 2 now. So we sort of have this nice disc shaped thing going on. So yeah, that was case 2. I hope you didn't have much problem understanding the contour deformation. I actually showed it. Many textbooks don't. But that's the advantage of my YouTube videos. I can actually draw this. Okay, moving on to the final case, case 3. Okay, case 3 now. I mean, you guessed it if you hadn't before. Z naught at the center, circle of A, circle of B, which I am drawing sort of a smaller radius, and then our contour, which will sort of include all of this. See, the formula won't change. That is the best part. It's a general formula for the coefficient. So dz prime 2z prime minus a minus b divided by z prime minus a, z prime minus b, z prime minus z naught to the n plus first power. Okay, let's do for negative n. Well, notice that for negative n, z naught won't create a problem, but a and b will, because now you're including them, unlike case 1 where we excluded all of them. So what we can do is sort of deform the contour again. I'm not drawing the entire deform diagram, I'm just drawing the small sub contours that we get around these singularity points. So the way we deform it, usually what happens is when we go in anti-clockwise, the sub contours go in clockwise. So we have C1, say this is around A, and say C2, which is around B, and I won't write the entire equation, but the idea is the same. Cauchy-Gursa enables us to write f of z prime over z prime minus z naught to the n plus first as a sum of these guys. C1, same integrand, plus C2, same integrand again. If you just multiply by 1 over 2 pi I, we get the expression for the coefficient. So if we sort of do it for C1 encloses A, so Cauchy formula, Cauchy integral formula for at A, plug in A basically at everything except z prime minus A, so we get basically the term we got before. A minus B and A minus B will cancel out. We just have 1 over A minus z naught to the n plus 1. This is just like case 2. And then for C2, we do a similar approach, except Cauchy integral formula for B. So the top guy will be B minus A, which cancels out with this B minus A. We have B minus z naught, B minus z naught to the n plus first, similar to this first term. So you have a sum of these guys. Okay, and this again is for negative n. Let's do for a positive, and positive is a little more work, like it always is. Okay, so positive semi-definite case going on here. We have now 3, because z minus z naught will also create problems, so we'll have 3 sub contours, C1, C2 as usual, because those terms are not moving from the denominator anyhow. So C1 about A, C2 about B, and I recommend drawing these sub contours whenever you're doing calculating the coefficients in the future, because it may be a waste of time to show the entire deformation, but a really good idea if we actually draw the sub contours like this. At least that's the way I did it when this was first taught to me, because now we can write this equation, contour equation about C as a sum about these 3 guys. So C1 dz prime f of z prime minus z naught to the n plus first, added with C2 dz prime f of z prime over z prime minus z naught to the n plus first, and then the C3 of course, which wasn't before, z prime minus z naught to the n plus first. And then for C1, well, nothing really changes. Now we can just multiply by the 1 over 2 pi I factor to get the coefficients. We get the same term as before, which is multiply by 2 pi I because of the formula, 1 over A minus z naught to the n plus first, and then the same term for the C2. See, that's kind of a good thing about these things, because some terms will be repetitive. Now for C3, notice we're sort of doing expanding around like z naught, doing contour integral around z naught. So this will, by the Cauchy integral formula, n derivative of which will give us 1 over n factorial nth derivative, just like for case 1 and case 2, of f of z, which is 1 over z minus a plus 1 over z minus b at z is equal to z naught. So what we have is these guys cancel out. 1 over a minus z naught to the n plus first. 1 over b minus z naught to the n plus first. Now using results from the past, from case 1 and case 2, we have negative all these terms. So negative 1 over a minus z naught to the n plus first minus 1 over b minus z naught to the n plus first. The beautiful thing is these terms cancel out. Sorry, giving us 0 for the positive semi-definite case. So you notice the symmetry going on here. For like the case where we didn't enclose any singularities, we got 0 for the negative terms, giving us a pure Taylor series. And now when we enclose all the singularities in the contour, we're getting 0 for the positive terms. We're getting non-zero for the negative power terms. So that's a cool thing about this. Okay, let me just expand f of z like we did in the past for this specific case where we enclose all singularities. So negative infinity to negative 1, we have a minus z naught, the n plus first. We just have negative terms, no positive terms. B minus z naught, n plus first. And then of course the z minus z naught to the nth power. This is the expansion. This in this case is a pure negative power expansion. Quite contrary to case 1, but that's how this thing works. Region of convergence is an interesting question, because now notice we don't have anywhere to stop. There's no like upper limit to this region. There's a lower limit, however. The circle of B, we can't go inside it, because if we go inside it will be between A and B, which will just be case 2. We can't go inside A because that will be case 1. So we are sort of at B and then again no bounds outside, because there's no other singularity sort of locus to bound us. So it's infinity. So z minus z naught, magnitude will be greater than B. That's the region of convergence. So just to draw it out a little bit, we have a circle of A, we have a circle of B, and the region of convergence is basically all that's outside B. Again, this drawing is pretty bad, but whatever. So sort of infinity shaded region. So I hope you see all the cases, the contour deformations. If you have any doubts, refer to my previous videos or shoot questions in the comment section. I'll be glad to answer. I hope you enjoyed this. Okay, so what's the take-home message from this? The idea is, well, in our function, the specific example, we had 2 major singularity points and also z minus z naught thing because of the coefficient formula, which also became a singularity for the positive semi-definite case. But the idea is, if you notice the pattern that was going on, we had the expansion point, we had a circle of singularity 1, let's call it number 1. We had a circle of singularity 2, call it number 2. And we would have also had, say, any other singularity circle if there were like another singularity, assuming there was something like 1 over z minus c. So which would have been, I don't know, singularity number n. Just keeping this process on. But the pattern or the idea of finding the coefficients of the Laurent series were that we had different coefficients, or we needed to take different cases as and when we included more and more singularity points. So in the most basic case number 1, where we didn't have any singularity points, we had a pure Taylor series with just positive coefficients. And then region between 1 and 2, when we included 1, include 1 we got another, we got a mixed Laurent series. We included 2, which was basically the final singularity point for this function that we did. And we got just the negative. But assuming we have, say, n number of these, then we'll again get a different mixed Laurent. And then if we are at the final case, so the nth one, when we include all of them, that's when we are getting pure negative coefficients, pure negative power coefficients. Because that's the end, and we aren't bounding ourselves, so we'll just get those negative ones, like an antithesis to the pure Taylor series for no singularity. So you see the general trend. We need to basically break up for different cases when we're calculating the coefficients, and we get the appropriate expansion in the appropriate region. So I think that's the entire take-home message from this example. And of course, we have our coefficient formula, which is basically this. And C again will depend on what case you take, and that's why I thought doing this example was important, because this teaches you how to consider cases. Okay, so I think this is it. So please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of gamma di gamma. Stay tuned for more content. I think I will be doing residual calculus, or maybe even classifying singularities. Let's see what happens. Stay tuned. Nevertheless, peace out.